Hello, everyone. My name is Shreyank, and I'm the Secretary for the Youth Science Organization. Today, I'll be giving you a brief introduction to quantum computing. This is the first part in a two-part video about this topic. Before we begin, however, let's learn about some fundamental ideas that will solidify our understanding of some of the later concepts. So first, let's talk about bits and qubits. What even are they? In computing, a bit is the smallest unit of data, akin to the elemental particle of the digital universe. Representing binary digits, bits can be 0 or 1, acting like switches that signify off or on states. Physically, bits are often electrical or optical signals, with low voltage or absence of light for 0, and high voltage or presence of light for 1. Despite their tiny size, bits form the foundation of digital information, enabling computers to store, process, and transmit data. Every text, image, sound, or video encountered in the digital realm is composed of a countless number of these bits, which is the reason every piece of technology we use today is functional. Over here on the side, we can see that there is a sort of conversion chart for decimal values to binary values, or vice versa. So a decimal value will be inputted, and the computer will process it as a binary value, and then it will be output as a decimal value usually. And these can stack up to make information like text, image, or sound, as previously mentioned. But the sheer size is absolutely unimaginable, but they still stack up to make lots of information that we encounter on a daily basis. So this is a qubit, and in contrast to a classical bit, which can only represent two states, a qubit in quantum computing can exist in a superposition of these states. And there will be more on that later. But it means that it can be both 0 and 1 simultaneously. This phenomenon arises from the principles of quantum mechanics, allowing qubits to encode and process information in a vastly richer and more complex manner. Additionally, qubits can exhibit entanglement, where the states of multiple qubits become correlated, enabling them to perform highly parallel computations and solve certain problems more efficiently than classical computers. While classical bits rely on definite states, qubits harness the intriguing possibilities or probabilities of quantum mechanics, which will be explained in depth later in this video. Now, a note about qubits and quantum computing in general is quantum computing doesn't necessarily make the calculations done faster, it just does it in a more efficient manner, in a more fluid manner, per se. And this will be covered in part two of this series, but that is a common misconception about quantum computers that quantum computers can completely replace regular classical computers, which isn't true at all. And we will be delving into more depth later on about this. So, basics of quantum computing. So, let's look at some basic quantum computing concepts before we begin. A superposition, as previously mentioned, is the simultaneous existence of multiple states in a quantum system until measured. Entanglement would be the phenomenon where the states of two or more particles become correlated in a way that the state of one particle instantaneously influences the state of the others, regardless of the distance between them. And quantum interference is when the phenomenon occurs where the probability amplitudes of different quantum states interfere with one another, leading to constructive or destructive interference, influencing the outcome of quantum measurements. So let's talk about superpositions. A quantum superposition is the foundational concept in quantum mechanics, describing the ability of quantum systems to exist in multiple states simultaneously. So, unlike classical systems, which typically occupy a single definite state at any given time, quantum systems can exist in a combination or superposition of different states until measured. Mathematically, this is represented by a linear combination of the basic states of the system. For example, a qubit, the basic unit of quantum information, can be in a superposition of both 0 and 1 states simultaneously. This means that until observed, the qubit is in a mysterious blend of both states, with each state having a certain probability of amplitude associated with it. Quantum superposition is a fundamental property of quantum mechanics and forms the basis of many quantum algorithms and technologies, including quantum computing and quantum cryptography. These both will be covered in the later video. So this is an example of a qubit, and this is an example of a classical bit. So you can see how classical bit it is represented by zeros and ones, and it can be either or. So it can be both at the same time. But a qubit is a blend of these. So this is an example of a superposition, but it's not limited to this, obviously. It could be over here. It could be over here. It could be anywhere within this qubit versus this, which is much more black and white in the sense that you can only be one or another value. And this is a lot more fluid in that sense. So using qubits, parallel arithmetic combinations are possible, and exponential multiplication per qubit is possible, and massive amounts of data can be handled in plausible, meaning efficient time. A common example of qubits or just quantum mechanics in general is Schrodinger's cat. So it's basically a thought experiment proposed by Austrian physicist Erwin Schrödinger in 1935 to illustrate the concept of superposition in quantum mechanics. In the experiment, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison, and a hammer. If the Geiger counter detects radiation, the hammer is triggered and it breaks the vial of poison and kills the cat. According to the quantum mechanics, until the box is open and observed, the state of the radioactive atom is in a superposition, meaning it's both decayed and not decayed simultaneously. As a result, the cat is considered to be in a superposition of being both alive and dead until observed, much like the qubit described earlier. To simplify, what this basically means is we don't know if the cat is dead or alive until it's observed. The atom placed earlier, is in a superposition much like this over here, which means that obviously until we look inside the box, we don't know if the cat is dead or alive. So in that logic, the cat is both dead and alive at the exact same time, much like the atom. Entanglement is a phenomenon in quantum mechanics where the states of two or more particles become correlated in a way that the state of one particle instantaneously influences the state of the others, regardless of the distance between them. This correlation persists even if the particles are separated by vast distances, violating classical notions of locality and suggesting a deeper interconnectedness between quantum systems. When particles become entangled, measuring the state of one particle immediately determines the state of the others, with their properties becoming perfectly correlated. This non-local connection between entangled particles has been experimentally verified through numerous tests, including the violation of Bell inequalities, and plays a crucial role in quantum information processing, quantum teleportation, and other quantum phenomena. So here is an example of one of the first instances of quantum entanglement ever captured. So you can see how all of these little particles sort of make this shape over here, but don't meet in the center over here, which means that they're attracted in a weird sort of pattern. And this is a very revolutionary image because it really shows us that quantum entanglement is in fact possible, which opens up so many possibilities in science and can allow for so many more breakthroughs. Interference is a concept where the probability of the amplitudes of different quantum states interfere with one another, which leads to constructive or destructive interference. This interference arises from the wave-like nature of quantum particles, such as electrons or photons, and is governed by the principle of superposition once again. When two or more quantum states overlap, their probability amplitudes combine, resulting in interference patterns that influence the outcome of quantum measurements. Constructive interference occurs when the probability amplitudes reinforce each other, leading to an increased likelihood of certain measurement outcomes, while destructive interference occurs when the probability of amplitudes cancel each other out, reducing the likelihood of their outcomes. So here's an example of interference. One famous example of quantum interference is the double slit experiment. In this experiment, particles, such as electrons or photons, are fired one by one towards a barrier with two narrow slits. Behind the barrier, there is a screen where the particles are detected. Surprisingly, Even when fired one at a time, the particles create an interference pattern on the screen, resembling the pattern produced by waves passing through the two slits. This phenomenon demonstrates the wave-particle duality of quantum particles and illustrates how the probability amplitudes of different quantum states interfere with one another, leading to observed interference pattern. The double-slit experiment is a classic demonstration of quantum interference and highlights the puzzling nature of quantum mechanics. So you can see how even though there are only two slits and two little particles fired, it makes this sort of pattern, which is something that is currently being figured out by scientists, but they still haven't gotten a complete hold of why this happens. So our second chapter would be types of qubits. And there are, in fact, multiple types of qubits in existence, but for this video, we will be covering just three main types. So that would be superconducting qubits, trapped ion qubits, and quantum dot qubits. So superconducting qubits are a type of qubit used in quantum computing, implemented using supercomputing circuits cooled to extremely low temperatures, typically near absolute zero. And these qubits rely on principles of superconductivity, where certain materials exhibit zero electrical resistance at low temperatures. In superconducting qubits, the basic unit of information is encoded in the quantum states of microwave photons, trapped in superconducting resonators. These resonators create an electromagnetic field that interact with Josephson junctions, which are nonlinear electrical components made from superconducting materials. The Josephson junctions serve as the building blocks of supercomputing qubits, allowing for the manipulation and measurement of quantum states. So this would be an example of a superconducting qubit, and these are usually stored in sub-zero conditions. So later in the later video, we'll give an example of how a quantum computer actually looks, and you'll see that it's stored in extremely cold temperatures because that's when these kind of things sort of fall into order and start working. Trapped ion qubits are basically a fundamental unit of quantum information encoded in the quantum state of an individual ion, which is typically held in place by electromagnetic fields. In this system, the qubit state is manipulated by laser pulses, which can effectively entangle multiple qubits and perform quantum logic operations. The qubit's coherence and stability are maintained through precise control of the ion's environment, such as its motion and interaction with its external fields. Finally, quantum dot qubits are a key constituent of quantum computing, leveraging the quantum properties of semiconductor nanostructures. These quantum dots, typically comprising a small number of electrons confined in a tiny region, serve as the basic units of quantum information. The quantum state of these electrons, such as their spin or charge, encode the qubit's information. By applying carefully tuned electrical and magnetic fields, researchers can manipulate the quantum states of the electrons, allowing for operations like superposition and entanglement, as mentioned earlier. Quantum dot qubits hold promise for scalable quantum computing due to their compatibility with existing semiconductor fabrication techniques and potential for integration into solid-state devices. Thanks so much for watching this video, and I will be releasing a part 2 for this soon. And this has been the Youth Science Organization. Thank you.